Now let me code the function LU without pivoting first. Okay, LU without pivoting, and then we can add the permutation matrix that perform partial pivoting later. Okay, let me call function. I want to have L and U. L for the lower unit, lower triangular matrix, and U upper triangular matrix. LU 7 B, and input A, the matrix A, and say that perform basic LU decomposition of matrix A, and no partial pivoting, and no permutation matrix, and when return, okay, you know that it return LU. So we start with I can have a blank here, like M N the size of A, and we expect that M should be equal to N. Now, M will be number of row and N number of column of A from the built-in function size in MATLAB. Now, when you input matrix A and array, the size return the dimension. Now, if not, you can show the error message. But in this case, now we're gonna make my code. I'm gonna want to make my code short, and then I initialize L by. Now initialize. I can have the comment initialize matrix L to be identity matrix. Okay, and I'm gonna the idea is that I'm gonna fill in a matrix L by multiplier that is negative value of matrix M. So for K, I have the index for the column I to n-1, right? We have moved from the first column to the column that is one column before the last one. The process here is to similar to Gauss elimination. We have two for loops, and then for I equal to K plus 1, and we're gonna want to do operation below the pivot, right? Now, if the pivot is K, so the pivot element is AKK, right? AKK is the diagonal, the pivot. K to N, and put something here, conclude with N, so have for the nested for loop. So what is here? I'm gonna find the factor and perform operation, right? And I know that I can fill in matrix L directly from the factor. So I can, instead of scalar, I can assign the factor. What is the factor? A I K divided by A K K. AKK is the pivot, right? And here you see that I don't have negative because I'm consider matrix L. So matrix L is very simple. I divide element of matrix A by the pivot in that corresponding location. And here would be L I K. Now, so you can see that LIK, we start with identity matrix, and then we store constant. Now, constant is multiplier that we use the multiplier is actually the element of matrix A that we want to eliminate, divided by the pivot. And I perform row operation AI K to N. Now row I, now column K to N. So this is vector. This is vector. And this is the row vector. Now we perform row operation A I K column N, and this add row I now will be modified by L I K, and the factor here you have the negative sign, right? Negative multiply A K column N. Now the pivot row, now row K, now column K to N. And that complete my decomposition, very short. And don't forget to assign A to U at the end of the for loop. A become the upper triangular matrix. Okay. So what should be my matrix A? A okay, 3 by 3, and okay, this is my matrix A. Let me save. LU, okay, I save it, and then I can call it. Okay, I start with matrix A. L is initially identity matrix, and then I fill in the first column. Now this come from 4 divided by 2, and then we perform row operation in the second row, and we eliminate. We make this element 0. And then I fill in the last row here by minus 2 divided by 2 over pivot. And after row operation, we have the first column, only the diagonal element that are non-zero. Then I fill in the second column of L, and then eliminate. Now this becomes 0, and that is my upper triangular matrix. Now you can verify that the L multiply U and matrix A same, right? You can verify. And there's a theorem that row operation does not change row operation, the process of forward elimination that we perform does not change the determinant. It means that determinant of A will be preserved, will be equal to determinant of U. And determinant of the upper triangular system is very simple. If you look at U, if you want to find the determinant of upper triangular matrix, it's a product of diagonal elements, and this is the basic linear algebra property. So you can the 2 multiply 1 multiply 4 is 8. And if you compare with that A, our matrix A, 8. So this is the byproduct. Now you can find the determinant of matrix A, very large matrix. If after operation, after the forward elimination step or after decomposition, by simply take the product of diagonal element of U. Okay, that's without pivoting. So how about with pivoting? Let me copy. Now copy this. I would call LUP. LUP. Now I'm gonna introduce the permutation matrix. Okay. LUP. And for the output, I want to know the matrix P. The permutation matrix. Okay. Perform LU decomposition and LU decomposition with partial pivoting. And we note that matrix P is the permutation matrix. And our linear system is actually PA equal to PAX to PB. LUX equal to PB. And PA equal to LU. Okay. Now we start with what do I do? Now, so I'm gonna initialize P identity matrix. Initialize matrix P. Permutation. As the identity matrix similar to L. Okay. And now this step is same, but I'm gonna include the similar to Gauss elimination. We're gonna include before we perform the elimination to include the partial pivoting, right? Partial pivoting. I'm gonna insert here before this for loop, because I know that this for loop perform operation, eliminate, perform operation. Partial pivoting. What do we do here? I'm gonna call the max, have dix and then index. Max gonna check for only the absolute value, ABS, absolute value of A from row K to the last row at column K. Okay, so I have check my bracket. Okay, that's correct. And IPR will be the index plus K minus 1. Now this similar to Gauss elimination. This nothing changed. If IPR not equal to K, we have to perform row interchange. So we're gonna, now my permutation matrix will be the now this statement means that we switch row K and row IPR of the permutation matrix. Now for all the columns, and you can see that we have the column here means that from column 1 to column n, and here we switch the entire row, row K and row IPR. I can add the comment, interchange row K and IPR of P. And that result in, oops, what did I do? Undo. Okay. My matrix A will be changed, right? We don't actually perform product multiplication. Now we know that A will change E and D N. N of partial pivoting. How do you think this is good? Good enough? So I check now before performing, you know that this for loop perform row operations, right? Now we create a metric P that keep track of row interchange. But we forgot something. We have to check that, okay, starting from the second pivot, if we find that we have to perform row interchange, we have to permute L, matrix L. Remember, we have permutation in front of L and then permutation transpose. We have to permute row of L as well. So we have to include this. If K, right, starting from step 2, if K is greater than 2, we have to permute L as well. Let me copy. This is L. And we're gonna switch only from column 1 to column K minus 1. Now before the current pivot, before we fill in, you have to switch the row of matrix L. Before you fill in any column K, you have to fill up to the K minus 1. This is L K minus 1. Now this is very important. And then we switch and then we let's say you are at the third pivot. Okay, before you fill in the third column, you have to interchange matrix L before you fill in interchange. So K, this case equal to 3, we have to interchange up to -1. So we have to consider to the second column. Okay. This is how we actually generate matrix L now without doing matrix multiplication. That's it. Now we think this is complete. Now let me check. Okay, let me clear. Okay, and then I have the same matrix A. And then I call this so this is what we have. This is matrix A. That's our input. And in my code, I don't use semicolons because I want to show you the result. So we have the big. Now index 2 means that the second row is the largest element. So here is my matrix P. Matrix A after row interchange will be this, and then you perform row operation. Now we're gonna fill in the first column of L. Now here we have 0.5 come from 2 divided by 4, right? And this will be -2 divided by 4. So we perform operation. So the second row is changed. And then L will be -2 divided by 4. Now it's -0.5. Now we fill in the first column. And then we eliminate the entry. Now the entry becomes 0. And then we move to the second pivot, second diagonal, second column. We check that we consider only the column below it. Even though 9 is larger, but we consider only the column, only the row below the pivot. Here we have consider only this. So we consider this vector indicate that the index is 2, and it corresponds to the row of 3, row 3. So we're gonna switch row 3 and row 2. It means that we have this. A. Okay. We have L. This. Now you can verify that PA equal to LU. PA equal to LU. So you can see that our system that you are going to solve using forward sub and backward sub, it's actually the rearranged system. The first equation comes from the second equation of the Now we can look at the P come from the second equation of the original system. And the second equation, now this is PA, that come from the third equation of the original system. And the last one comes from the first equation of the original system. Hope now that's not too difficult for you. Nah? We simply add the permutation matrix, and every time you permute P, now you want to permute means interchange P, you interchange A, and don't forget to interchange L before you fill in the multiplier at the current step. Okay. And one application is that we want to find the inverse of matrix A. Find A inverse. And if you want to find A inverse, you know that this mathematical is necessary. So it means that you have, I can write this is my unknown. Now my unknown, I have unknown. Now it means that A multiply my x1, the first column of A inverse as the unknown x2 up to xn. I can write the first column of identity matrix, the second column of the identity matrix up to the last column. This is the, I use this symbol to represent the first column of identity matrix. It's actually I1. What is I1? I1 is actually 1, 0, 0 up to the I2. What is I2? 0, 1, 0, and then, okay. So you can see that you can solve. Now you can solve for column, for column 1 to column n to get. Now, it's like you have A. Now you have the problem that AX1 equal to I1, right? AX2 equal to I2 up to AXN equal to IN. You have n systems, and every time that you get this is the column of A inverse, actually, right? The column of A inverse. So every time you change the problem, if you use Gauss elimination, you have to go back to augment matrix and perform forward elimination. But if you have LU decomposition, LUX equal to I, you only perform decomposition 1, and then you can save the computational cost. And you decompose A into L and U only one time, and then to solve this system, you only perform forward sum and back sum. Now the operation cost involve the decomposition of factorization is order n cube. The order involves the forward sum and back sum. Triangular system is only n square. Now I will talk about that later, next class. But you can see that when the system is large, forward elimination step take the majority of computational costs. So if you use Gauss elimination, you have to, it's not convenient. LU decomposition is the practical one. And this is the one that used by MATLAB backslash LU decomposition for general matrix A. Another thing that about determinant of matrix A. Now we can the property that you should know, the property that you should know is that we have P A go to LU, right? Previously you have A equal to LU, right? And you have determinant of A. Determinant of A equal to determinant of L multiply determinant of U. And determinant of L is 1, right? Because determinant of triangular matrix is the product of diagonal. Determinant of lower triangular matrix, determinant of upper triangular matrix, or determinant of diagonal matrix is simply the product of diagonals. So what is the diagonal of what are the diagonal elements of L? 1, right? So that's why I told you that det A equal to det U. Determinant. Right? But now here without permit, this is the basic LU. And here we have the partial pivoting. So how do you find that? We're gonna have det P now from definition of det, now det of product. It's a product of det L and det U. And det L is 1. And that U is the product of diagonal. In mathematics, we use the pi. If you call summation, it's a Greek symbol. Now summation, we have addition, right? Addition, summation. But here we have pi as a product of UII. I from 1 to n is a product. This represents the product of diagonal elements, diagonal entries of U. And we want to find determinant, right? And so with the permutation matrix, you see that we have this. What is determinant of P? Anyone has an idea? What is the determinant of identity matrix? 1, right? Because the identity matrix is actually diagonal matrix with all elements equal to 1. It's 1. So what is that P? Now we can prove that it's equal to that P equal to -1 our S. Now where S is called the signature. This is the difference because you have permutation matrix. Now what is signature? It's equal to -1. Now when if number of elementary permutation is odd, equal 1. If number of elementary permutation is even. So what is elementary permutation? It means that when you perform a series of permutation matrix, anytime now when permutation matrix is not identity matrix, that is count 1. You understand? So if we go back to our example here, Where's my example? Okay. Now we start A and 3 by 3. So at the first step, this is not identity matrix. So P1, now we count 1. And in the second step, we also permute, right? It's not identity matrix, right? P2. We count 2. That's all. We have only 2 permutation matrix and all not now, and every permutation matrix is not identity matrix, right? So we have 2. So in this case, S is 2. So I can show you that det of A is actually det of U that I obtained. You can verify that. So this is the meaning. So when you perform like you have P1 to Pn and you count only the case that the step that P is not identity matrix, and that would be your elementary permutation. You count. Okay, that's the meaning of this. Okay, let's go back. We have some time left. Okay. So I want to have my code being able to find determinant. I want to my code to get the signature. Do you think it's interesting? So I want to get S as one of my output. S. So what do I do? Now I may before everything I add to here S equal to 0. My initial count is 0. And every time I have to perform permutation, I'm gonna do the summation. I'm gonna increase. Now S is called signature. Number of elementary permutation. So I only need one more statement. Where do I put in my code? Where do I put? Over there? Over here? Where? Which line? Which line that I should put? Which line? Within if clause here, right? If IPR not equal to A, it means that I have to perform row interchange. So I'm gonna S equal to S plus 1. Increase by 1. And that's it. Okay, let me try okay, save and let me clear everything. Clear CLC. With that, we can find the determinant. My matrix A 3 by 3. Okay. And I don't want to see intermediate step. I make have a semicolon. Okay, semicolon. Want to get only the final result. Semicolon. 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 Okay. Save. I will call function and okay. This is my result. L, my lower triangular matrix. Now we have previously verified that the product of L and U equal to permute matrix A, PA. So if I want to find det of A, 8, right? Right. What is my signature? 2, right? So I can show you that det of U. What is det of U? What is my U? U here, right? The product of 4, 8. I can show you this diag U. This is my 4, 1.5, 1.323. It's about 8, right? Yeah, my code can provide S, and you can relate det of A and det of U exactly. You have the sign. That is the LU decomposition that can be applied to any matrix A that is non-singular. That is non-singular. If you apply the partial pivoting and at any step, and you found that you cannot avoid a 0, it means that your matrix is singular. If you during the process, even you add the partial pivoting, you find that you have the problem of division by 0, it means that your matrix is singular. You cannot find the unique solution. Okay. But if you don't apply partial pivoting, you may have the problem of division by 0, even if matrix A is non-singular. Okay, that concludes today lecture. Now, for any non-singular matrix, you can find a unique solution with LU decomposition with partial pivoting. So I'm gonna write the function that perform forward substitution and backward substitution to get the solution vector X. Now let's call the LU solve 67B. Okay, and my input will be LU and B. I have 3 inputs variable or input argument. The lower triangular matrix, that actually the unit lower triangular matrix, the upper triangular matrix, and the right hand side vector B. Let me solve LUX to B, where L is the unit lower triangular matrix, L lower triangular matrix, U upper triangular matrix that we obtain from the decomposition process, and B. I have start with the size of L. It can be size of U, the size, and D is the 0 in row 1 column. Now I initialize the vector D, column vector D. Now we define vector D as the vector of the product of UX. And X, now our solution, zeros in 1. Okay, let me B is the right hand side, right? Column vector. Now column vector. And X is a solution vector. So the first step, now we will perform forward subs to obtain vector D. The first step, forward sub. To solve LD equal to B. To solve for D from the linear system LD equal to B. Now the forward subs. Now we begin with the first equation. That D at the first element equal to B. First element divided by L11. And then I start the for loop. For the, I represent the equation number or row number. For row to n, you're gonna find di. I subtract by L. Bi is the right hand side, right? B2 is correspond to the second equation, right? So we multiply. Here we're gonna find actually the summation of Li from the first column to the column I minus 1. This is actually the row vector. We have metric L. Now we consider L at row I from column 1 to I minus 1. So this is the row vector. And we multiply with the column D from the first column to the I minus 1 column. And then subtract by the LII. Actually, LII is 1. And then we end the for loop. Now the for loop will repeat. Start from I equal to 2 from the second equation, and then increment 1, 3, 4, up to the last equation, and we get the vector D fill until the last element. Once you get vector D, now we can perform backward sub to solve for X from Ux equal to D. This is our definition, right? D equal to Ux, we define D as a Ux. So we solve, now D is known now, so we can solve for X. Now this is identical to the Gauss elimination backward sub. Now this step, you have seen this step before. Xn, we start with the last equation with only one unknown Xn, the last unknown Dn, divided by, not A, UNN. Diagonal. Now we're gonna fill now we initialize 0, now 0 vector, and then we fill in the last element of X, and then we use the for loop. That's n minus 1 with the increment of -1 up to the first equation. Xi Xi start from x at n-1. Okay, and here we have di. Vector d now is on the right hand side. Now subtract by the summation. We can see that the summation is give you scalar. Now we have the product of row vector and column vector. We have scalar. It's the same meaning. So it's gonna be ui I plus 1 to n. Now add the equation I. Now we take column I plus 1 to n to the last column, multiply with x. Now column I plus 1 to n. Now this is the summation. You have row vector multiply with column vector. You have summation. You have scalar, and divide by u I. Notice that ui is not equal to 1. The diagonal element of u can be any number. If you want to see the step, I can let's start without showing only the final results. So we have vector x. Now that would be the output. Okay. So now we can solve complete the LU decomposition. Let's start with the example A. I have the 4 by 4 matrix A and B. The column vector. I will call. Let me save this. Save. You solve. Okay, 7B. Okay. I'm gonna decompose matrix A. I'm gonna decompose matrix A using this function. We perform PU, LU decomposition with permutation matrix. Now here is my matrix L, matrix L, matrix U. Let me move the window. Oh, it's difficult. Okay. U and P. And we recall that we have PA, which is equal to LU, equal to PB, right? Now PB, not B. So now we can, and here we have now we have lower triangular matrix and the upper triangular matrix. I'm gonna call LU solve this the function LU solve 67 this year, and I have create the new function. I have B here. to avoid the confusion with the previous function. Okay, here I have to call PB, right? Don't forget P here, because LU equal to PA. Okay, what's wrong? Oh, okay, 0 is wrong. Zeros. Okay. And here's my vector X, my solution. Now you may want to compare with MATLAB built-in function. Now MATLAB has the built-in function LU. LU is a built-in function in MATLAB. Okay, now I can move the command window up. LU, we can call this and let me use another variable L U P. I use the lowercase, and we compare with our result. Now you will see that we have the same result. This is L. Now L is a unit. Now lower triangular matrix. Now this is U. And the upper triangular matrix and P. Okay. Now you can check the determinant of matrix. Determinant of A, 12. And determinant of U. Determinant of U is a triangular system, and is a product of diagonal. And we can verify that that U. And let's use our result that U and S. So S is you recall that we have that A equal to -1 power S, right? Right, power S times that U. So here we have same that A 12. Now -1 power 3 is the negative. Negative times that U is the negative, become positive.